We'll end 3.1 and 3.5 with a couple of ideas. The first one is the 5% rule for independence. This is a situation where you have with replacement, without replacement, and in this specific case, when we're sampling and thinking about the probability of something without replacement, and your sample size is less than 5% of the population, right? When you're choosing, right, these samples, then you can pretend you're sampling with replacement. It simplifies our calculations to do so, because the sample size is so big. Our sample size is so small compared to the population that the replacement or without replacement really doesn't matter. The effect on the probability is small enough that we just don't care, right? And to check, you divide the sample size by the population. If it's less than 5%, then you can just assume that it's with replacement. Here's a straightforward example where we can use the 5% rule. If 40 of the subjects are randomly selected, find the approximate probability that they all had negative results, something like that, right? And so in this case, looking at the table here, we had 1,000 in this table. What's the probability if you select for it that they all had negative results? 40 out of 1,000 is 4%, which is less than 5% of the population. So we can assume independence. And so then you can say 866 over 1,000 times raised to the power of 40. And in that case, again, where are we getting the 866? That comes from right here, the total amount that tested negative. And then you're going to do it 40 times. This is as opposed to saying 866 over 1,000 times 865 over 999 times 864 over 998. You don't have to do that. You could use the 5% rule and just assume everything is with replacement, and it simplifies your calculation. And so we have that. Let's take a look at example 11 as a practice problem. Here's contingency. Here's a table here that we're looking at with the different variables. Those who are accepted, waitlist, turned away, totals, and then their ethnicities for that situation here. And so go ahead and practice real quick, pause, and then try to answer those questions, and I'll put the solutions up. Okay, so this is what you're calculating here. The probability of being accepted in white, number of accepted total, and white, right? So accepted in white would be 316 out of 1750. The probability of being Asian or accepted. So the probability, it's an or, so this one's going to change our situation. Probability of being Asian. So how many Asians are there? We have 299, so that would be 299 out of 1750 plus being accepted. That total is 920 out of 1750. And then you have an overlap. You have the and part of being Asian and accepted. So there's 120. And so this is where you have to subtract out because there's an intersection between those two events. So that would be 120 minus 1750. So in this answer here, that would be 299 plus 920. So that's 1219. I'm going to do this another way. 920 minus 120 is 700. 700 plus 299. So your answer is 999 over 1750. And then the probability of being black, given that you were accepted. How many were accepted in this case in total? There were 920. Given that you were accepted, what's the probability of being black? And well, it's black or Hispanic. I think we should be going here. So that would be 484 out of 920. And so that's what you would have there. It's a good practice problem that goes through the different rules here. And then we end on tree diagrams. Take a look at how this is done here, and then we'll answer this question. Take a little bit you may pause and look at the two solutions that are already done here for you, the two examples, and then we can do that one in the middle. There we go. Maybe it looks better. Or look at your notes there. And so what you're doing is just kind of guiding out, mapping out the scenario. So what is the probability that the person misses the flight? And so you have these probabilities, right? And then what you do is you multiply through the branches. So 0.24 times 0.05, 0.76 times 0.02, and you get that there. Same thing about this situation here is you multiply through the branches here. And in this case, though, what's the probability that he went to Hawaii? And so in this case, well, we'll come back to that one. Let's finish this one here. And so the numbers are built in for you already. And so in this case, what is the probability that any given person will test positive? Okay, so go ahead and think about that. So what we're looking at here is the probability that that any person tests positive, right? And so we look at the outcomes. There are two branches, right? 0.033 times 0.94 plus, that's this branch here, where you're going to there, and then the other branch is here and here. And so from there, 0.967 times 0.044. And so then that will get your probability there. When you do that calculation, you get 0.074 with that. And then this last one's a more complicated problem, but you want to keep in mind a probability is always, again, about what you are, what's possible is the denominator here. So you see Joey after the weekend, notice he's burned pretty badly. What's the probability he went to Hawaii? So first you want to find the probability, right, what you want that he went to Hawaii, 0.40 times 0.90. He went to Hawaii and got sunburned. And then divide it by the possible, right? And then you count what's the total probabilities that he got sunburned. So he stayed home and sunburned. So this is your total. This is your Hawaii sunburn, and this is your home sunburn. And so when you put those numbers together, multiply, the probability is that, again, you see Joey after the weekend and notice that he's burned pretty badly, right? So it's kind of like a given. What's the probability that Joey went to Hawaii given, right, that you see he's sunburned badly? And so that's why you have this kind of unique situation there.